we're going to look at the area and distance problems. And basically what that is we're trying to find the area under a curve. So here in these drawings here, in this multiple choice exercise, we have this same curve in all 4 drawings, and we're trying to estimate it using rectangles. The instructions say, by reading values from the given graph of f, use 5 rectangles to find a lower, okay, so the key here is lower estimate at 5 rectangles into the curve. Okay, so this has more than, these both have more than 5 rectangles. Okay, so they've got 10 rectangles, so you can just count those out. And then the other one is lower estimate. If you find the area of these rectangles, they're going to be more than the area that's under the curve. Okay, but if you find the area of these rectangles, that's going to be less than the area under the curve, because you can see that this area here, this area, this rectangle is less than this area right there under the curve, and so on. Okay, so this will be a low. So this graph here will give us a lower estimate. Okay, and it's got 5 rectangles. This will also give us a lower estimate, but it's got 10. So this is going to be the one we go with. These are above, so that's not going to work. Okay. So yeah, once again, so the idea is lower estimate means the area that's under this curve here will include these areas here as well. Okay. But when we're estimating using these blue rectangles, we're not including that area. So we're going to definitely get a value that's less than the area under the curve. So it'll be a lower estimate. Okay, so let's go ahead and figure out what we need to do is figure out the area of each of these rectangles. Now, the area is equal to the length times the height. Okay, now all of these lengths are 2 for every rectangle. For every rectangle in this figure right here. Okay, so that means that the length part is going to be 2, and then the height part, we just need to find the heights of each of these, and you just kind of have to estimate it. This one may be 3.7, so that's 3.7, and then this one right here, it might be like about, it looks like it's just above 2, so I'm going to say 2.1. Okay, so 2.1, 3.7. This one looks like it's just about under half, so I'm going to say 1.4. And this one looks like about 0.8 maybe, and this one maybe 0.5. Okay. And if I calculate that out, I end up with, on a calculator, I end up with 17. And so that would probably work for this one. If you got a slightly different answer, then, you know, like maybe one of these values is a little bit different than what I put, then you're probably still going to get it right. Okay, let's go on to the next one. Part B, I guess. Or it doesn't really have, not really by parts. Okay, so let's take a look at what they're asking for here. By reading values used, okay, so again, it's 5 rectangles. That means we're going to throw out this and this because these have 10. And then you want to find a upper estimate. Okay, so that means that you're going to go with this one here. Okay, and throw that out. So we'll go with this one right here, and you just kind of look at what the values are. This looks like about 6, and this one looks like about well, it's just the values from last time, really. 3.7, 2.1, 1.4, and just from last time's values, and 0.8. Okay, so the area is going to be, again, the length is 2, and the heights are 6, and 3.7, and 2.1, and 1.4, and 0.8, and that comes out to be approximately 28. That comes out to be about 28. So 28 would be the answer right here. And then they have these parts right here, find new estimates using 10 rectangles in each case. So here they want a lower estimate. So here's 10 exercises. So we'll just use this one for the 10 rectangles, and they're under the curve. Okay, so we'll use this one for the lower estimate. And so again, you just kind of try to figure out what those are. This looks about 4.7. This one maybe there's 3, there's 4. It's a little bit more than half, so 3.6, 2.8, 2.2. I was just guessing here, just estimating. At 1.4, this looks like about 1.1, maybe just 1. It's really close to 1. Maybe you could probably put 1.1 and get away with it. 0.8, 0.7. You don't have to be exact. Okay, so then the length here is 1 for each of these. Each of these rectangles is now length 1 instead of length 2. So 1 times, just add them all up. So 4.7 plus 3.6 plus 2.8 and so on. And I get 19.4. So I'll put 19.4 there. Then this upper estimate, this looks like a good one for the upper estimate right here. And this is going to be a 6. 4.7, because these are each of these rectangles is bigger than the corresponding area under the curve that's in that slot. And then this goes all the way down to 0.7. So I added those up, and again, it's going to be 6 plus 4.7, 3.6, and so on. And I get 24.7 approximately. And if you go a little bit different, you'll probably get the same. You'll probably get it correct, even if you're a little bit off the answers that I have. Okay, so let's go on to number 2. Okay, here we have a function. F of x is 6 plus 4x squared. Okay, so now here there's an actual values right here. Okay, so estimate the area under the curve of f, the x-axis and the lines x equals -1 and x equals 2. So here's x equals, this line right here is x equals -1. And this line here is x equals 2. Okay, so they're specifying the boundaries. So you have the x-axis, the curve, no, the lines under the curve, so everything under the curve. So they're looking for this area here, that's here. Okay, now these blue areas is a little bit different. Okay, but now this is they want us to do R3 and an R6. Okay, so R3 means 3 rectangles, and it means use right endpoints. Okay, so here, this first rectangle is off because it should be using this point right. This should be, so for this interval here, this rectangle should be using this right endpoint, should be using this point to determine its height. Okay, so this would be good. This is good right here. It's using the correct one there, and that one's using the correct one there too. This is using wrong. Okay, these are both wrong. Okay, for the second interval, it should be using the right endpoint as well. And that's fine. It is. Okay, it is for there, it is for there. Here it's not. It should be using that one for this one. So this is off. Okay, so it's going to be this one, and then this right endpoint here, it's using that to determine the height for this last rectangle. Okay, so it's using its right endpoints. That's what R means. The R means. Okay, now what we can actually do is we know what those right endpoints are. This is 0, that's 1, and that's 2. So if we make a table with x values, 6 plus 4x squared, and we just have to calculate 0, 1, and 2. And if you put a 0 in here, you're going to get 6. You put a 1 in, you're going to get 10. If you put a 2 in, you're going to get, what's that, 4, 16, 22. Okay, you're going to get that. Okay, and so the area, remember the length is 1. Each of these lengths is 1, okay? Let me circle that so there can be no doubt. These are out. And so then you take the height of the rectangles. So 1 times 6, that's the area of the first one. 1 times 10, that's the area of the second one. And 1 times 22 is the area of the third one. Okay, so you add those together, you get 38. That's 38. Okay, now we're also supposed to do R6. Let's go to the next page for that one. Okay, so that means right endpoints. And 6 rectangles. Okay, so here, this is the right endpoint here. This is the right endpoint. This is the right. It looks like this is it right here. It has 6 rectangles. So it appears that this one is the one. This one's not using the right endpoint, so that's out. This is not using the right endpoint, so that's out. This one is definitely not using the right endpoint, so that's out. Okay, so it's going to be this first one right here. Now here, these lengths are 1/2. Okay, so you have to be a little bit more careful. Okay, now, so these are going to be the right endpoints with the axis, and then our f of x. What was it? 6 plus 4x squared. Is that it? Yeah, 6 plus 4x squared. Okay. Okay, so the right endpoints, this is negative 1/2. What is that? Oh, holding the pen wrong. Okay, this one is 0. This one is, so these are the right endpoints right here. 0.5, 1, 1.5, and 2. Okay, so plug those numbers in, and let's see, what are you going to get if you put a, okay, so I put a negative 0.5 in here, then, oh, this is going to be 7. I put a 0, and that's going to be 6. I put a that in, that's also going to be 7. I put a 1 in, I get 10. 1.5 is going to give me 15, and 2 is going to give me 22 again. Okay, so the area is going to be 1/2 times the sum of all these. So 33.5 is what I got for that one. And so that will be 33.5 for that answer there. Okay, let's go on to the next part. Okay, so now here this is left endpoints. Okay, so L3 means left and 3 rectangles. Okay, so this is not using the left endpoint, so throw that out. This is not using the left endpoint, so throw that out. This one is using the left endpoint. This one's not, so throw that out. This is using the left endpoint, and so is that. So they're all using the left endpoint, and there's 3 rectangles. Okay, so so the left endpoints are -1, 0, and 1. Okay, so these are the left endpoints right here. So we're not using the 2. We're using the -1, but instead we're starting at -1 first, but when we're not using the 2. Okay, so this is going to give us 10, 6, and 10. So the area, and again, the length is 1 again, so the area is going to be 1 times 10 plus 6 plus 10. And that turns out to be 26. Okay, so that answer will be 26. Okay, now the second part is use 6 rectangles with the left endpoint. Okay, so this one right here is not using the left endpoint. So throw that out. This is not using the left endpoint. This one is using the left endpoint. This one's not. Okay, so we got to know it's got to be this one, and you can confirm that all these left endpoints are being used for this one right here. And so this is going to be the answer to the first part. And then we're using these values here for our left endpoint. So we start with -1. And then -0.5, 0.5, 1, 1.5. And we don't use the 2. We don't use the 2 though. Okay. So those are 10, 7, 6, 7, 10. And 1.5 gives us 15 again. Okay. So the area is going to be 1/2. Here the length is 1/2, so that goes right there. And then, so this first rectangle, the height is 10, the length is 1/2. So it's 1/2 times 10, that's going to be 5. And then the rest of them. Like that. And that works out to be 27.5. So we go back to here and 27.5. Okay. Now the next one is this one right here. And this one is, okay, so M3 means 3 rectangles and use the midpoint. Okay, so you're looking at the center point here. That's not using the midpoint. This one is not using the midpoint either. This one's not using it either. So yeah, this one is. Okay, so this first rectangle is using the midpoint. This rectangle is also using the midpoint, and this rectangle is using the midpoint. Okay, so they're all using, all the rectangles are using the midpoint. Okay, and so, and then here's the function. It's what was it? 6 plus 4x squared. So here the midpoint was, here the midpoint is 0.5 or -0.5, and then this is 0.5, and this is 1.5. Okay, so, and when you put the values in, you're going to get 7, 7, and 15. Okay, so the area is going to be 1, which is the length is 1 again, because you're still going from here to here. Okay, so that's still going to be 1, and then 7, 7, and 15, and that adds up to 29. Okay, so that will be the the first one, 29. Okay. For the midpoint. Okay, now we're supposed to find M6 also. So you're going to look for M6. So 6 points and use the midpoint. So this is not using the midpoint. This isn't either. So throw that out. This isn't using this midpoint, so forget that. And this one isn't using that midpoint. And it's got some weird writing underneath too, so that's suspicious. This one's using that midpoint. And this one, so this rectangle is using that midpoint. This rectangle is using that one. And so on. Looks like these are using the midpoints of each of these intervals, okay? Okay, so midpoint, now this is going to be a little bit more tedious because the midpoints are now, it's between -1 and -0.5. So that's actually -0.75 is that midpoint there. And then this one is -0.25. And then this is +0.25. And then +0.75. And then +1.25, and then +1.75. Okay, so if you put these values of x in here, you get the following. You get 8.5, 6.5, 6.5, 8, 12, and 18. Okay, so the M6, again, the lengths are going to be 1/2 because from -1 to -0.5 is 1/2. Right. So, and then these are the corresponding heights of the rectangles. And I added them together and I got 29.75. Okay. So, let me see here. Okay, 29.75. Okay, then the last one they're asking a kind of interesting question, and that is right here, is part D. Which, from your sketches, which estimate appears to be the most accurate? Okay, so let's kind of look at these. This one right here, you kind of look and see what you're over and under shooting it by. Each of these rectangles, it looks like you've got some area here that's being counted too much, but you have some right here that's left out. And then the same thing for this one. So, and it looks like each rectangle kind of balances out its errors. So you have an error here where it's under, and you have an error here where it's counting too much. Okay, so it shouldn't be counting this area, but then it should be counting this area, but it's not, in other words. And each of those rectangles has that happening. So this is looking like a pretty good estimate. It's actually going to be the correct answer, because if you look at R6 and L6, let me see here. Okay, so we go to, in fact, maybe, okay, we got it right here. This one right here is actually R6, the drawing for R6, and this is actually the drawing for L6. So if you look at L6, then you have all these rectangles. You've got all this area here that should have been counted but wasn't, and you have a little bit of area here that was counted that shouldn't have been. So this kind of balances out a little bit, but I mean, both of those areas is probably like that area, and so then you still have these two to deal with, and so then this is going to be off. Same thing over here. You've got well, this is the opposite over here actually with R6. These areas are counted too much. And then you got these areas here that aren't counted enough. But these two areas is probably, might not even be, it's probably less than what this area alone here is. And so you got these, so this is overshooting it, what the actual area under the curve is. Whereas this, so this seems to be the most accurate. So just looking at the different pictures. Okay. So that's the answer to the previous part too. Okay, great. Any questions on that? This is kind of an interesting section. I think it's pretty straightforward what you're supposed to do. Hopefully straightforward. Okay, so let's look at exercise number 3. Here you have speedometer readings at 10-second intervals during a 1-minute period for a car race in the Daytona International Speedway in Florida. So at these different times, the velocity was recorded from the speedometer. Okay. So part A, estimate the distance in miles the car traveled during this time period using the velocities at the beginning of the time intervals. Okay, these velocities are in miles per hour, and we want to find how many miles. So that's good. They're at least the same kind of units. But these times here are in seconds. Okay. So for part A, estimate the distance during this time, but using the velocities at the beginning of the time intervals. This is the beginning of the time intervals. So from 0 to 10, you're going to be using this one. From 10 to 20, you're using that one, and so on. So for that one, you're going to be using just these ones right here, not that one. That one's not going to get used in this one. That's not, that information is not going to be used in part A. Okay. So the beginning of the time intervals, this is like the L6 is what this is. Okay. So so what I'm going to do is I'm going to add up all of these right here. So the answer is going to be, for this one, is going to be you add up all these. Okay, notice I'm not including this last one, not including the last one. I've got 6 values here representing the 6 time intervals. Okay, those add up to 860.9. Okay, now this is this represents each of the speeds over here. Now, each of these is over a 10-second interval. So if I go, so for example, if I go 183 miles, no, I see. Okay, 10 seconds is well, there are 60 seconds in 1 minute, right? And then there is 60 minutes in 1 hour. And so seconds will cancel, minutes will cancel. So I have this 10, and then maybe this will cancel with one of those. So I have 1 over, let's see, 6 times 60 is hours. So 10 seconds is equal to 1 over 360 of an hour. Okay, so I'm going to take this 860 and I'm going to multiply it by, so this is miles per hour. Okay, and I get approximately 2.39139. I get something like that. So I'm going to put in 2.391 2.91. That's rounding it to 3 decimal places, okay? Just to the third decimal place right there. 2.391. Okay, now this other one is another estimate using velocities at the end of the time period. So this one, you're gonna take and add up 168 plus 106.6 all the way to the, and you're gonna actually, this one you're gonna use the last one, okay? And those add up to 851.9. And then I'm gonna take this 851.9 miles per hour, and then I multiply that by 1/360 hours. And that's approximately 2.3655. Looks like we're repeating 5. So 2.366 be the answer there. Okay, so C, are your estimates, upper and lower estimates? Explain. Okay, now if you kind of follow the pattern here, it's 183, it slowed down to 168, then it slowed down more to that, then it slowed down to 100, then it sped back up, right? So the speed was maybe going like this. And so using left or right endpoints is not going to help that much. And part B is the correct answer. The velocity is neither increasing nor decreasing. So the estimates are neither upper nor lower estimates. Okay, let's look at number 4. The graph of the velocity of a braking car is shown. Use this graph and a midpoint Riemann sum with 6 equal estimates, subintervals, to estimate the distance traveled by the car while the brakes are applied. Okay, so we get to do 6 intervals. There's 6 seconds, so that's great. So these will be the intervals right here. And for this first interval, we'll use this mid value here. Try to look where the mid is, maybe there. For the second interval, we'll use the midpoint here. And the third interval, the midpoint there, and so on. So we just try to find the middle point, and that is what we're going to try to find this rectangle like that. That's what Riemann sum is. It means this. This is just midpoint. That's just M6. Okay, is what we're trying to do. Riemann sum using the midpoint. That's M6. What we've been saying all along. Okay, so what does the height look like? That looks like about, wait, that's, hold on a second. I think I figure out what this is. Okay, so the midpoint, it's actually maybe right there. I'm gonna just say, dang. This one looks like above, so I'm gonna say maybe that's 85, and maybe that's 65 is the height here. And here, I'm gonna say, I don't know, 42. This would be 45 right here. That's a little less. I'm going to say 42. And then here, maybe, wait, no, it's just, wait. This one here, maybe 25, maybe, I'm just guessing here, 15, and then maybe 8 there. Just kind of looking over here. This is 15. This line is 15. That looks like 15. This looks like maybe 8, maybe 7. Okay, so the length is 1. Okay, so I get about 240. If you get something that's close to that, then it's probably also going to be correct. I know that, like, for example, 230 also works. Okay, now, the area, so definition, the area of the region S that lies under the graph is the limit of the sum. It's just the limit of the sum of the areas of approximating rectangles. Okay. So so basically what happens, so it's just imagine this, okay? You're making, so instead of doing, so like if we go back to, let's go back to this one right here. So here we use 6 rectangles, and this is a better estimate than using 3, or generally, you know, sometimes there could be like little flukes or something where it's not, but this is generally better than using 3. And if you use 12, you're generally going to get a better outcome. And then if you use 1,000,000, you're generally going to get pretty good. You're going to get even better than estimate than what that is. And so, yeah, so the more that you use, the better. And if you take the limit of these as you go to infinity, and if f is a continuous function, you take the limit of these as then goes to infinity, then you're going to get the exact value under the curve. Okay, and the limiting value is going to be the exact value. Okay, so if you can imagine like millions of these little rectangles and you're summing them all up, then that's the outcome. And you can actually calculate that in a lot of cases. Okay, so for example, right here, we can actually calculate what that is. We can actually calculate what the M, so basically using left endpoints, that's going to be Ln, and using right endpoints, that's going to be Rn. So you can calculate those values right there. Okay, so in other words, let me rephrase that differently. If these are the left endpoints right here, these x1, x2 are the left endpoints, then this part right here is going to be Ln. Okay, because and then the length of each curve is this right here, is the delta x. Okay, and you're taking the interval from A to B, you're taking its length and dividing by n, and that's the length of each sub rectangle. Okay, and so these are the L's right here. It's just distributed. You could factor this delta x out. You could factor the L out. Okay, and we just have the L and R, just like we've computed it in the previous exercises. Okay. So for the left endpoints, here's how you calculate the left endpoints. Okay. So here we have a specific example. The first thing that you want to do is you want to take the interval and calculate delta x. Okay, that's b minus a over n. Now, b is 8, a is 6. Okay, so that's going to be 8 minus 6 over n, or 2 over n. That's going to be your delta n. Okay, your delta x, I mean. Okay, another way to look at it is just take, what's the length of this interval? It's 2. So your subrectangles, they're going to have length 2 over n. If you want to have n of them. Okay, so there's going to be that delta x right there. There's going to be 2 over n. So basically, it's delta x. I think I shouldn't put this as the answer. Delta x, f of x, I. Okay, as I ranges from 1 to n. Okay, so this is going to be 2 over n, and then f of xi. Here's your f. So for right endpoints, we're going to use this right here. A plus I delta x. But A is 6. That's going to be 6. And then delta x is that. So 2I over n. I'm going to use that. Okay. So those are going to be our xi's. So here's our f. So we put these guys in to, and for the x's right here. Okay. So that's going to be 6 plus 2I over n squared plus, and then put this into here. Like that. Okay, and this is going to be the answer. And that's kind of sloppy, but yeah, that's going to be the answer. Okay, let's do number. Okay, so I'm just putting these in for here. This goes into there, and this goes into here. Okay, so those get, each of these x's gets replaced by that, and that's why this expression is here. So I have all this squared plus the square root of 1 plus 2 times all this, 1 plus 2 times all that. And that's all multiplied by the delta x, which is 2 over n. Okay, so let's look at number 6. Determine a region whose area is equal to the given limit. Do not evaluate the limit. Okay, so here we have this right here. So, so let's see. What we can look at is if we compare with this right here, okay, comparing that, then it looks like this piece right here would be our delta x, and it looks like this piece right here would be our xi's. Okay. Okay, so xi would be I pi over 8n. And again, it looks like it's going with the right endpoints. Since it's not like some number plus this, then that's probably indicating that A is 0, meaning the left endpoint has to be 0, which would be this one. So this one, and this one have left endpoints that are 0. This doesn't, and that doesn't. So I could probably safely throw those out. Okay, so now if it's the intervals from 0 to pi over 8, let's see. 0 to 8 pi. That's probably not that one. Okay, so 0 to pi over 8. This part in the front, yeah. So here with each of these, the lengths are or I should say, for each of those, b minus a is pi over 8. Okay, so that would give us a delta x of pi over 8n. Okay, so delta x would be pi over 8 divided by n, which is pi over 8n. Okay, which is right here. Okay, so that's consistent with that. And then tangent of, and that would mean that our xi's would be 0 plus pi I over 8n. So pi I over 8n would be this. These would be our xi's right there. So it's going to be this last one.